transportation industry is undergoing an autonomous revolution, but for these systems to achieve mass adoption, they must be more than just capable, they must be safety proven. In autonomous navigation, every millisecond is a measurement of distance. At 60 kilometers per hour, a 100 millisecond delay in processing is nearly 2 meters of travel. This reality demands a fusion of silicon and software capable of significant, safety-critical decision-making. When it comes to collision avoidance, there's zero room for computational lag. To ensure this reliability, the underlying system must be incredibly compact. AVs need a kernel that is lean enough to guarantee that when a failsafe triggers, the hardware responds instantly. In this project, we evaluate if the compact, deterministic nature of ChibiOS can serve as the reliable backbone for next-generation AVT operations.
For our project, we chose to explore the capabilities of ChibiOS. The term Chibi is a Japanese slang term similar to pipsqueak in English. Like its name suggests, ChibiOS is a small-form, real-time operating system designed to utilize as little memory as possible for use in microcontrollers. ChibiOS provides a multitude of RTOS features while being able to run on limited memory. These features range from preemptive multithreading, support for up to 128 priority levels, and task synchronization. Systems like FreeRTOS are also capable of these features. However, ChibiOS varies in how they are handled. In FreeRTOS, for example, when tasks are created, they are dynamically allocated in memory, whereas ChibiOS utilizes static memory allocation at compile time. Because it occurs at compile time, ChibiOS allows for more predictable memory usage, which is important for systems where SRAM is limited. Because of its use of static memory allocation, which helps keep memory usage low, it allows for more efficient execution of multiple tasks, even when on constrained hardware. ChibiOS supports up to 128 priority levels, whereas FreeRTOS does not enforce a strict maximum. This gives both systems flexibility in how tasks are scheduled. Task synchronization is also supported in both systems. These features are handled very similarly between operating systems, including support for semaphores, mutexes, and priority inheritance. This allows for shared resources and communication between tasks. One main difference between ChibiOS and FreeRTOS involves hardware interaction. On its own, FreeRTOS does not include drivers, making it reliant on external libraries depending on the used hardware. ChibiOS, however, includes a hardware abstraction layer and built-in drivers for peripherals. This makes ChibiOS a more integrated and plug-and-play system compared to FreeRTOS. We chose to implement ChibiOS on an Arduino Nano board. The Nano has limited SRAM and flash memory, which makes it a strong platform to demonstrate the strengths and capabilities of ChibiOS. ChibiOS involves static allocation, built-in integration, and low resource usage.
This code implements a rate monotonic scheduled system using ChibiOS, designed to demonstrate sophisticated real-time features like priority inheritance and deadlock prevention on the resource-constrained Arduino Nano.
The first line of code here attaches the ChibiOS library to the script. This includes several built-in features that we have gone over already, for example, mutexes. Next, 5 built-in timers are created. Add a touch of realism. We're using these timers so that if a task misses its deadline, it will immediately go into the fail-state mode at the instant of the deadline. Then, the mutexes for resources X and Y are created. With ChibiOS, you have to allocate memory in the form of a stack for each task manually. Here, we are using 128 bytes for the simple tasks and 256 for the tasks requiring resources, as the code is a bit more complex, and we want to avoid a stack overflow. Here's our function for when a deadline is missed. It defines the pins and then sets them all to high. It will then enter an infinite loop, essentially shutting down. This is our visual cue that a task has been missed. Now let's get into the tasks. Task 1 has the shortest period, and as we are scheduling with the rate monotonic method, it will be of the highest priority. The loop for this task begins with checking the current time and orienting itself to that time. Then it sets its alarm. The built-in function for alarms allows us to pass it the timer, how long the timer should be set for, and what function it should jump to if the timer is missed. Next, to show that the task has begun work on the CPU, the LED is set to high. To demonstrate a task, we are directly commanding the ALU with NOP, which means no operation. It just takes up the CPU's time for a certain number of cycles, just like a real task would. Loop gives the no operation command 8,648 times to simulate a busy CPU for 20 milliseconds. This was calculated from the speed of the clock and how many cycles the operation takes. When the task is complete, the LED is set to low, indicating that it is finished. Immediately after, the alarm is reset and the next deadline is calculated. Then this particular task is set to sleep until the next time it is instantiated. This means that the task won't be seen by the processor until the sleep timer is over. Tasks 3 and 5 are very similar to task 1, just the periods and the execution times have changed. However, for tasks 2 and 4, there is additional code that makes them reliant on resources X and Y. Instead of the simple loop in the previous tasks, where it just cycles through the no operation cycle until it completes its execution time, these tasks lock resource mutexes before. For example, in task 2, it does its work with no resources for 4,324 cycles, and then it locks resource X, does another 4,324 cycles, locks resource Y, another 4,324 cycles, and finally unlocks both and does its last 4,324 cycles. Each of these sets of cycles corresponds to 10 milliseconds. Additionally, since priority inheritance is not directly supported with ChibiOS, we decided to make the task lock resource X before it is allowed to lock resource Y. Task 4, for example, it has no need of resource X at first, but it must lock it before it can use resource Y. This is to prevent deadlock, and we will modify the code to show a deadlock occurring later on in the video. With the tasks explained, we move into the last parts of the code, initialization. First, control is transferred to the ChibiOS kernel here. The mutex objects are created, and the tasks are instantiated as well. The priorities of each task are manually added here, in accordance with rate monotonic scheduling. Once this main thread is done running, it enters an infinite sleep loop. This just makes it so the processor never sees this code again and focuses on the tasks indefinitely.
We begin the demonstrations by pushing the system to its breaking point. Task 1 is set to 20,000 iterations. Because it is the highest priority task, it starves the lower priority tasks of execution time so aggressively that a deadline miss is triggered in under 1 second. Next, we drop the workload to a stable 10,000 iterations. Here, the 16 MHz processor handles the multitasking with ease. There's an ample slack time for every other task to meet its deadline indefinitely. Finally, we find the danger zone at 18,000 iterations, triggering the safety state after approximately 3 seconds of operation. After multiple iterations of testing, the longest execution time for task 1 was found to be 36 milliseconds, and for a 100 millisecond period of the task, 36% of CPU utilization. Beyond this threshold, task 1 starves the system and triggers a deadline miss. In the context of AVT, task 1 is our steering actuator controller. Task 5 could be a battery temperature monitor. While the steering system requires frequent updates, there is a specific CPU usage sweet spot that must not be exceeded, as to not starve any lower priority tasks such as battery thermal management. Here, we demonstrate priority inversion using tasks 2, 3, and 4. We begin with task 4, the lowest priority task of the 3. In this scenario, task 4 acquires mutex X, then nesting further, acquires mutex Y, before performing its work and releasing both. It's important to note that task 4 only requires resource Y, and just puts a lock on resource X first to follow the alphabetic resource protocol. Above it sits task 2, the highest priority process in this group. Task 2 follows the same mutex logic. First, mutex X is locked, then task 2 runs for a bit. Then Y is locked, then task 2 runs for a bit, then both X and Y are released. Finally, we have task 3, a medium priority task that shares no resources with the others. It simply demands CPU cycles. In an AVT system, task 2 could represent obstacle avoidance systems, task 3 could be the infotainment/UI system, and task 4 could again be the battery thermal management system. Here, priority inversion occurs when task 4 holds mutex X and is preempted by the medium priority task 3. Because task 3 doesn't care about mutex X, it can run its entire workload while task 4 is still holding the keys to the resource that task 2 needs. Without a solution, our critical obstacle avoidance task 2 would be forced to wait for a low priority task 3. To demonstrate this, we focus on the workload of task 3. When we set task 3 to 80,000 iterations, the failsafe initiates after only 3 seconds, indicating that the system has detected a deadline miss. However, when we run the system below this threshold, we observe that task 2 successfully meets its deadlines. The deadline miss observed when task 3's workload exceeded 80,000 iterations serves as a clear demonstration of unbounded priority inversion. The increased execution time of the medium priority task 3 delays the lower priority task 4 from releasing a shared mutex. This created a blocking dependency that prevented the high priority task 2 from accessing the required resource and time to meet its deadline.
Okay, so this code has been running for a bit. This is just the code we had before. I've omitted the fifth LED for simplicity, but the code for the fifth LED is still running on the processor. LEDs 2 and 4 are currently sharing resources. I'm going to modify the code so it no longer mandates that a task locks resource X before Y in all cases, and we're going to see a deadlock occur. And in our code, a deadlock just looks like all the LEDs lock on high. I commented those lines out, and now I'm going to update the code. As you can see, task 2 ran first and used resource X. Then task 4 ran and used resource Y. Task 4 needs X to complete, and task 2 needs Y to complete. Eventually, the deadline for task 2 or task 4 is missed, and our missed deadline chunk of code takes over to clearly show deadlock occurring. More sophisticated approaches can be taken, like priority ceiling protocol, but in this case, alphabetic priority protocol works just fine too. Alphabetic just means that you have to lock the resources in alphabetic order, such as X before Y.
This project utilized ChibiOS to demonstrate deterministic execution in a multitasked environment. We attempted to ground the task synchronization concepts into reality by mapping the 5 firmware tasks to real-world AVT functions. Ultimately, while ChibiOS served here as an excellent platform for mastering rate monotonic scheduling, true AVT implementation requires a shift from simple deterministic kernels to more complex safety-certified microkernel architectures as outlined in this peer-reviewed research.